Hello, Chem 111. This video is about the Rydberg equation. We'll cover both what it is and how it's used. Briefly, before we get into that, I want to talk about why it was developed. So in the late 19th century, early 20th century, it was developed to explain the emission spectra of elements. And we use it to calculate the wavelengths or energies of spectral lines in the emission spectrum of a particular atom. And it turns out that this particular equation works well for hydrogen, but less so for atoms with more than one electron, for reasons that we'll get into later. Just as a reminder, an emission spectrum looks something like this. I can't never draw my brackets right. Which I've drawn to approximate the emission spectrum of the hydrogen atom in the visible range, so from about 400 nanometers to 700 nanometers. And what we see is a series of four lines with different colors because they have quantized or a single wavelength. Okay. For a much better demonstration, take a look at this YouTube video that demonstrates the emission spectra of a series of different elements. So it's easier to understand what we're looking at from that video. All right, so recall from a previous video or from class the Planck-Einstein relation, which relates the energy of a photon of light to its wavelength by Planck's constant and the speed of light. It turns out that through the Rydberg equation, we can also relate this to a constant called the Rydberg constant and specific electronic transitions between different energy levels within the hydrogen atom. So here I'm going to use N to indicate the energy level in which the electron is found initially, so N sub I, minus the energy level where the electron reaches finally after it transitions. I just want to specifically define these variables. So R sub H is the Rydberg constant. Okay, it is constant equals to 2.18 times 10 to the minus 18th joules. All right. The nice thing about writing R sub H is that it reminds us that this is specific to the hydrogen atom and we can't use it for atoms with more than one electron. All right. N sub I is equal to the integer associated with the level where the electron was initially. All right, so the integer of the level that the electron was initially in, and then N sub F is the integer of the final level where the electron ends up. Okay. All right, I've got the Rydberg equation rewritten here. And before we jump into some calculations, I just want to think about this pictorially for a second. All right, let's say we've got a hydrogen atom, and I've got drawn here various energy levels that electrons can occupy in that hydrogen atom. And let's just say for argument that we've got our atom in a bulb to do an emission spectrum, and let's say the electron is hanging out here in N equals 3, so the third energy level. Right. At some point, that electron will fall down to a lower energy level, so a N equals 2 or N equals 1, for example. So let's just say it falls down to N equals 2. When it does that, it's going to a lower energy level, so it will release energy in the form of light. Right, so if our electron ends up here, we have relaxed, and we're giving off energy in the form of light. Okay? So we could use the Rydberg equation to calculate the energy that is lost when that electron falls from n equals 3 to n equals 2. So let's go ahead and do that. So delta E is equal to R sub H, which from a few minutes ago I told you was equal to 2.18 times 10 to the minus 18th joules, times 1 over n sub I squared. So in this case, n is equal to 3. So 1 over 3 squared minus sub squared. So if we plug that into our calculator, I get negative 3.028 times 10 to the minus 19th joules, right? So I want to make a couple of notes here. One is we get a negative value for our energy. If we're going to report the energy of a photon, it can't have negative energy, so we take the absolute value, right? What that negative is telling you, though, is that the atom is losing energy as that electron relaxes back to a lower energy level, okay? So a negative energy actually means that this is an emission process. The electron is going to lower energy and giving off light, right? But again, if you're going to use it to report an energy of light or a wavelength, we're going to take the absolute value. So just make a note. All right. So I've drawn an emission process where the electron falls from a higher energy level to a lower energy level. It turns out that this also works in reverse. If we hit an atom with light of the right wavelength, we can bump an electron up an energy level. The atom can absorb energy and promote an electron to a higher energy level. So I'll just draw that really quick. All right, so I've redrawn the energy levels here. Let's say we start with the electron in n equals 1, and we hit that atom with light of the right energy to promote the electron up to n equals 2. Right? We can also use the Rydberg equation to calculate the energy that was needed to bump up that electron. So here we would say delta E is equal to 2.18 times 10 to the minus 18th joules multiplied by 1 over 1 squared, because we're starting in n equals 1, minus 1 over 2 squared, because we have ended at the n equals 2 energy level. And if we plug this into our calculator, I think what you should get is 1.635 times 10 to the minus 18th joules. Okay, so we have a positive energy here, which means that our atom is absorbing energy. So this is an absorption process. We are bumping an electron up an energy level. All right. Again, we could then use this energy to calculate the wavelength of light that was needed to promote the electron. Let's do a practice problem. So calculate the delta E for the transition from the n equals 4 energy level to the n equals 3 energy level for the hydrogen atom. My question for you is, can we see this transition with our eyes? And remember that the visible range is from about 400 to 700 nanometers. So go ahead and pause the video, work this out, and then you can check out my answer. All right, let's do this. So delta E is equal to hc over lambda, which is equal to r sub h, just rewriting the Rydberg equation here, over n sub I squared minus 1 over n sub f squared. Great. Let's plug in the numbers. So 2.18 times 10 to the minus 18th joules times 1 over 4 squared. We're starting out in equals 4 minus 1 over, 3 squared. Plug that into the calculator, and we should get negative 1.060 times 10 to the minus 19th joules. Right. Remember, we're going to take the absolute value of this so that we can calculate lambda. Right. So delta E is equal to 1.060 times 10 to the minus 18th. All right. So that's the answer to the first part of the question. So the next part is, can we actually see this transition with our eyes? And the way we want to answer that is to determine the wavelength, I wrote minus 18th back up here. I wanted to write 19. All right, so going back, the way we want to answer this is to relate the energy to the wavelength using the Planck-Einstein relation. Is equal to hc over lambda, and like I did in a previous video, I'm going to rearrange this equation to solve for lambda. All right, so if I do that, lambda is equal to hc over delta E. Let's plug in our numbers. So recall that Planck's constant is 6.626 times 10 to the minus 34th joules seconds. Speed of light is 2.998 times 10 to the 8th meters per second. All of that over our energy, which is 1.060 times 10 to the minus 19th joules. All right, just to make sure that our units cancel out, we have joules and joules, seconds and seconds, so we're left with meters, which is great because that's what we want. And if we plug all of that into the calculator, you should get 1.874 times 10 to the minus 7th, I lied, 6th meters. Okay, so I can't really tell you right there if we can see that or not because we have units of meters. So I'm going to go ahead and convert this into nanometers by taking 1.874 times 10 to the minus 6th meters and multiply that by 1 nanometer over 10 to the minus 9th meters, which gives me 1,874 nanometers. That is well outside of our visible range, so we can't see this electronic transition. So just a couple of reminders. Rydberg equation is used for the hydrogen atom only, not for anything else. And it allows us to calculate the energies and wavelengths associated with the electronic transitions in the hydrogen atom that appear in the emission spectrum.